Welcome to Tomorrow Unveiled, where we dissect the future one layer of source material at a time.
And this week, wow, we are really witnessing the moment technology stops being just an accessory. It's starting to become an extension of us. We are quite literally getting strapped into the future.
That's absolutely right. And our focus today is wearable tech, but, we really have to move past that old idea of wearables 1.0.
Yeah, the step counters and the simple sleep trackers. That's old news.
Exactly. For Tomorrow Unveiled, we are diving deep into the foundational breakthroughs that are, well, they're dissolving the boundaries between our own physiology and digital function.
It's a transition into what our dedicated research team is calling embodied computing. It's about seamless, zero-latency integration. The tech is becoming so integrated it's almost invisible to you, but the effect is, it's profound.
It is. So our mission today is to synthesize the most corroborated findings from the research compiled for the period of December 11th through the 18th, 2025. And this was a really pivotal week.
It really was. Not because of big consumer product launches, because those were, mostly on pause.
Right. It was pivotal because the underlying infrastructure, the hard science, just accelerated at an astonishing pace.
The focus shifted entirely. It went deep into the infrastructure. We're talking new biomaterials, breakthrough neural interface architectures, and the complex engineering needed for high-speed, on-device AI.
These are the literal building blocks for the next decade of our personal tech.
No question.
Okay, so we've organized the source material around three primary layers of this human-machine integration. These themes just kept surfacing in the data. We'll start with the neural layer.
The mind.
Then I'll move to the optical layer, which is all about vision and augmented reality.
And finally, the somatic layer. So the body itself, electronic skin, intuitive touch.
And then we'll wrap up by looking at the huge legal battleground that all these breakthroughs have suddenly created. Okay, let's unpack this. So the most profound and maybe even a little unsettling changes are happening at the neural frontier. We've moved completely past just passively recording things like brainwaves. Now we are actively closing the loop. We're connecting thought directly to action.
And the sources confirm this is moving so fast. It's going from a research experiment into a clinical, even commercial reality.
And that clinical adoption is accelerating for sure. I mean, the activity we saw this week from regulatory bodies, that's definitive proof.
Absolutely. Yeah. Our dedicated research team noted that in mid-December, a non-invasive ALS neuromodulation device actually received FDA breakthrough device designation.
And that designation, for anyone who doesn't know, it's designed to fast-track novel therapies. So things that have the potential to provide a much more effective treatment for, life-threatening or debilitating diseases.
It signals a massive governmental commitment to deploy these BCI-related therapies and to do it quickly.
Okay, so that's the clinical side. But let's talk about the raw technical speed. This quest for sub-100 millisecond latency, it's being won right now.
It is. The research team highlighted a massive milestone from collaborators in China. They successfully implanted an invasive BCI system into a quadriplegic patient.
And the result was a thought-to-action delay of under
100 milliseconds.
100 milliseconds. Okay, let's put that in context. That number sounds small, but what does it really mean?
Well, it's fascinating. If you, an able-bodied person, are asked to press a button the moment you see a light turn green, your physical biological reaction time.
Right, the time for the signal to go from my eye to my brain to my hand.
Exactly. That's typically between 200 and 250 milliseconds.
Wait, so you're saying the BCI augmented user with this interface is reacting 2 to 2.5 times faster than the human biological standard?
Precisely. They are, in effect, creating a hyper-reflexive control loop. By translating the patient's intent directly from the motor cortex to, say, a wheelchair or a robotic arm, it's bypassing the damaged spinal cord entirely.
So for tasks that are mediated by the system, the BCI user could theoretically have faster physical responses than an able-bodied person.
They can. And it's a staggering technological reversal.
And the sources indicated this wasn't just some fleeting lab success.
Not at all. The system successfully enabled the patient to do real-world things, controlling a robotic dog to go get takeout, navigating a wheelchair outside in complex environments.
That suggests a level of reliability that goes way beyond just a proof of concept.
And that reliability is the absolute key, because historically BCI systems have suffered from this crippling problem called neural drift.
Okay, can you explain that simply for us? Why does the signal degrade over time? What does that mean for the person using it?
So think of it this way. Your brain is incredibly dynamic. It's plastic. Neurons shift how they fire, maybe a little scar tissue forms around the electrodes, or just your overall brain state changes because you're stressed or tired. So when you first train a BCI decoder, it learns a specific pattern for, say, move left. But if that pattern subtly shifts an hour later, the decoder breaks. It doesn't work. And the user has to go through this long, frustrating recalibration session.
So it works great for a half hour, and then the brain just moves at the goalposts, and the tech is useless until you retrain it?
That's neural drift.
Yeah.
And that's what the CAS team addressed.
What was the fix?
They tackled it with two core software innovations. The first is a computational technique called neural manifold alignment.
Okay.
Imagine your raw neural data is like standing in a blizzard. It's chaotic, it's high-dimensional, it's noisy. But if you could project that blizzard onto a 2D map, you'd find that the underlying patterns, your fundamental intent, always follow a stable, lower-dimensional roadmap, a manifold.
So instead of trying to read the chaotic, raw signal, the algorithm is smart enough to find the consistent underlying pathway of what you're trying to do, no matter how much noise is around it.
Exactly. This alignment ensures consistent decoding. And the second innovation is online recalibration. This is a dynamic learning algorithm that just updates the decoder in real time as you use the device.
So no more lengthy daily calibration sessions.
Gone. The system just adapts to you on the fly. It's ready to go the moment you are.
So that's the speed and reliability side covered. But speed is nothing if you don't have a massive amount of data to process. And that brings us to the second major front, the bandwidth war.
Highlighted by the Columbia BISC implant project.
What's so revolutionary here is the architecture. The Columbia BISC project, that's biological interface system to cortex, it completely redefines how a neural interface is physically built.
They managed to collapse the entire complex signal chain, the electrodes, the amplifiers, all of it, onto a single CMOS chip.
Okay, let's slow down on CMOS. For listeners who aren't familiar, CMOS technology is the manufacturing standard for basically every modern chip, right? Your phone, your laptop.
Pretty much everything.
Yeah.
And building this on standard CMOS architecture means two critical things: scalability and cost reduction.
So they can use existing, cheap mass production techniques.
Right. They completely sidestep the delicate, cumbersome bundles of wires that you usually see connecting electrodes to these bulky external processors. It's integration taken to an extreme.
And the numbers that came from the research team on the density they're truly staggering. I mean, traditional arrays might have, 96, 100 electrodes?
100, maybe. The BIC project achieved 65,536 electrodes on one tiny chip.
65,000.
Which is about 650 times more density than the traditional arrays. It's a monumental leap in resolution.
So this jump in resolution moves us from listening to the roar of the crowd, where you're just averaging the activity of thousands of neurons,
to listening to the individual conversations happening inside the cortex. This is true neurocartography. You're mapping the brain's function at this incredibly fine-grained level.
And crucially, the form factor addresses the long-term safety concerns. The device is paper-thin.
Only 50 micrometers thick, about 3 millimeters cubed. And this is key. It's non-penetrating. It sits softly in the subdural space, just under the durameter.
And why is being non-penetrating so vital for long-term health?
Because when an electrode penetrates brain tissue, even tiny movements of the brain can cause microtrauma. That leads to scarring, cell death, and the signal just gets lost over time.
Which limits the functional lifespan of the device.
Hugely. This flexible floating array approach avoids that trauma. It means the functional lifespan of this implant could potentially be decades. And that's a prerequisite for any kind of consumer or widespread clinical adoption.
Right. You can't have a device that needs major surgery every few years. And what about getting the data out?
The research team noted that connectivity is also a massive leap. We're talking 100 megap's wireless bandwidth.
So they can read all 65,000 plus electrodes and do it quickly.
That 100 megabits per second is a huge improvement. It confirms the future isn't just about reading the brain with high resolution. It's about doing it quickly and reliably enough to capture nuanced thought patterns and stream them out without a bottleneck.
Okay, so connecting all this, the speed, the density, the reliability, to the bigger picture. These leaps have created an urgent legal crisis. The question of mental privacy is now a legislative necessity, not some philosophical debate anymore.
That's the critical transition. If the tech is this intimate, the law has to catch up. The research team highlighted a coordinated legislative push, especially in states like Montana and Vermont, to establish neuro rights.
Like a Bill of Rights for the human mind.
Exactly. And it's distinct from standard digital privacy because it's addressing the involuntary, deeply personal nature of neural data.
And the most critical clause being proposed is the conscious bypass clause. So prohibiting companies from using BCIs to execute decisions by bypassing your conscious decision-making.
That clause hits the hyperreflexive CAS breakthrough directly. If the BCI predicts and executes the intent to turn the wheelchair 150 milliseconds before you're fully consciously committed, has it bypassed your conscious will?
That's a huge question, and it's not just for paralyzed patients. Imagine a pilot augmented with BCI controls.
Or a consumer driving a BCI-controlled car. That gray area where intent and action merge, that's where the future of this human-AI symbiosis is going to be defined. And it's going to be defined in the courts.
But our research team also raised a significant concern with the existing legal proposals. They're calling it the inference loophole. So the laws might strictly define neural data as brain recordings, direct EEG signals. Is that definition tight enough to actually protect our privacy?
It raises a profoundly important question. The data compiled by our team suggests that companies could just harvest the same valuable mental state data using proxy metrics from less regulated wearables.
So a smart ring or a watch doesn't need to read your brainwaves to know you're stressed or anxious?
Not at all. It can infer that mental state with high accuracy from things like your heart rate variability, eye tracking, skin conductance, all data collected by consumer devices right now.
So if the law only focuses on the source, the direct brain reading, it completely ignores this mountain of other data that gives just as much insight into your cognitive and emotional state.
Precisely. The current regulatory gaps could let companies harvest this high-value mental state data for marketing, for insurance scoring, for surveillance, all while claiming they're compliant because they aren't reading the brain directly.
The law would be fighting the last war while the real battle for privacy happens on our wrists. If the neural layer is all about the speed of intent, then the optical layer augmented reality is about the speed of reality. And this past week, we saw a definitive shift in focus. It's all about solving the core usability issues of AR.
Latency and ecosystem fragmentation.
Exactly. The dominant theme here is the latency imperative. In AR, lag isn't just annoying.
No, lag kills immersion. It causes what's called perceptual drift, and critically, it causes nausea and headaches. The whole industry is focused on getting the user experience to a point where the digital stuff layered on the physical world feels truly physically real.
And that strategic shift is really embodied by the Android XR strategy and the unveiling of Project Aura.
This is a collaborative strategy. You've got Google, XReal, Samsung, even eyewear leaders like Warby Parker and Gentle Monster.
So it's Google's attempt to unify the very fragmented AR software market, just like Android did for mobile phones years ago.
Fragmentation has been a killer for developers. If every headset runs a different OS, you just can't justify the investment. So Project Aura is the unified reference design for that ecosystem. And its architecture is built for one thing: speed.
And it does that with a dual-chip architecture. It splits the workload between a general processor, the Qualcomm Snapdragon,
Which handles the OS, the Wi-Fi, the apps.
and a custom XReal X1S spatial computing chip. So what does separating the workload like that actually achieve? Why can't the Snapdragon just do it all?
Well, the trade-off is a little more energy use, but the benefit is performance specialization. The Snapdragon is a great generalist, but the X1S chip is a specialist. It's dedicated solely to the physics of light, motion prediction, and rendering.
So by offloading that heavy, specialized task, the X1S can just run a tight, highly optimized loop without any of the general OS overhead getting in the way.
And that specialization delivers the one metric that matters most: 3 milliseconds of motion to photon, M2P latency.
3 milliseconds, that number is the heart of the breakthrough.
It is. M2P measures the delay from when your head moves, the motion, to when the display updates the image in your eye, the photon. For context, early AR devices were struggling to get below 40 milliseconds.
Which is what causes that swimming, laggy feeling, the perceptual drift.
Exactly. Even high-end tethered PC VR systems only recently got below 12 meters. So by hitting 3 meters, the research team highlights that this is the effective threshold of believability.
At that speed, the digital hologram updates so instantly with your head movement that your inner ear, your vestibular system, it doesn't detect a mismatch between what you see and what you feel.
Which eliminates the nausea and the user fatigue that plagued all the earlier devices. It's a brilliant strategy from Google. They're providing a high-speed, stable hardware target for developers, and that just lowers the barrier for the next generation of truly functional AR apps.
But the best ecosystem needs powerful, miniaturized components that can fit into frames that, look like normal glasses.
Right. And that brings us to the hardware enabler, which our research team identified. OmVision's microdisplay. For years, the bottleneck was balancing super high resolution, a wide field of view, and decent battery life in a small, socially acceptable form factor.
And the OP03021 LCOS microdisplay seems to solve that bottleneck.
It does. This component delivers an impressive 1632 by 1536 resolution at a 90 Hz refresh rate, all packed into a tiny 0.26-inch format. LCOS is liquid crystal on silicon. It's a reflective technology.
And here's where it gets really clever on the technical side, the part that solves the form factor issue. It integrates the control logic and the memory directly onto the display silicon.
That integration is the key. It's what minimizes size and power draw. Traditionally, those would be on separate chips, connected by tiny wires that consume power and take up space.
But combining everything onto the same piece of silicon, they dramatically reduce the power consumption and shrink the physical footprint.
Which means the next wave of consumer AR glasses in late 2026 can finally look less like some industrial prototype and more like stylish eyewear from partners like Warby Parker. It enables that zero-footprint, all-day wear goal.
Okay, so moving from hardware to utility, the AI Copilot is what really defines the actual experience of wearing these things.
And we saw constant iterative improvement on existing hardware, like the Meta Ray-Bans update V21. These updates show AR moving beyond just being a screen overlay. It's focusing on contextual awareness.
And the V21 update has a clear focus on accessibility and context over just flashiness. Tell us about the conversation focus feature.
That feature uses the open-ear speakers and the microarray in the glasses to do some advanced localized audio processing. It actively isolates and amplifies a speaker's voice in a noisy room while aggressively suppressing the background noise.
So it's basically a high-tech hearing aid, but packaged in a consumer form factor.
It's a massive accessibility breakthrough. And then you have this Spotify visual integration. This is a pure context example. The onboard AI analyzes what you're looking at, say a band's logo on a shirt or an album cover, and it contextually plays matching music.
It's making the environment reactive to your perception without needing a display at all.
What's fascinating here is the dual-track market strategy that's unfolding. While Project Aura is aiming for high-fidelity visual immersion, there's a simultaneous push for these pragmatic, low-weight utility devices.
Like the LL Vision Leon Hay 2, which the source is detailed. It weighs only 49 grams.
49 grams. That's featherlight. Perfect for all-day wear. And its primary focus is real-time translation and transcription via a lightweight large language model running locally on the device.
The assistant-first approach.
Exactly. The user doesn't need a complex 3D interface. They just need immediate context, real-time communication help. This lightweight model is probably going to see rapid adoption in enterprise, education, and tourism before high-fidelity AR even hits critical mass.
So this divergence is leading to a clear market split. And our research team notes Google's plan for 2026 confirms this.
It does. They plan to launch the high-end display-based Project Aura alongside a separate, streamlined line of AI smart glasses that are audio and camera only, like the current Meta Ray-Bans.
So the market is splitting into visual AR, the high-res immersive experiences, and audio AR, which is all about hands-free AI interaction and contextual hearing.
Both are designed for all-day wear, but they serve fundamentally different needs.
Yep.
That's a major signal for developers.
We've covered intent at the neural level and vision at the optical level. Now we move to the final layer of integration, the body itself, or what the research team is calling the somatic web. And here we're seeing breakthroughs that turn our skin, even our clothes, into continuous self-powered interfaces.
And this segment tackles one of the most persistent hurdles for pervasive wearables, power autonomy.
Right. If a device is meant to be paper thin and totally flexible like a temporary tattoo, you can't plug it in. You can't replace a battery.
It has to power itself continuously, from the environment or from you.
And the Boise State breakthrough details exactly how this zero-maintenance power goal is achieved with the MEZE tattoo. Let's break down the material science here.
So the tattoo uses emazines. These are 2D inorganic compounds, titanium carbide, specifically mixed into a flexible polymer. Emazines are remarkable because they're highly conductive. They're also extremely flexible and durable.
And crucially, this conductive circuit integrates a triboelectric nanogenerator, a TENG.
Right. TENGs sound like sci-fi, but they're based on a very old principle.
Can you give us a clear analogy for the triboelectric effect?
Sure. Think back to when you were a kid. rubbing a balloon on your hair to create static electricity.
Okay, yeah.
That is the triboelectric effect. It's the transfer of electrical charge between two materials when they touch and then separate. A tang is just engineered to capture that energy from friction and motion. In this case, as you move, your skin stretches and relaxes, and the thin layers of the e-tattoo separate and reform.
So the energy is harvested directly from my normal daily kinetic activity, walking, stretching, even just breathing.
Precisely correct. That continuous motion generates a distinct electrical charge that's harvested and stored in a little micro-supercapacitor that's integrated right into the material. The result is zero burden monitoring.
It requires absolutely zero maintenance or external charging. It's entirely parasitic, but in the best way possible.
It lives on you, eats the energy from your own motion, and provides real-time health data like ECG and EMG with no user intervention at all. It's a massive step toward pervasive infrastructure-level health monitoring.
But once you have the power source, you still need a safe and precise way to manufacture the circuit, especially if you want to apply sensors directly to the skin.
And that's where Linköping University's innovation comes in, light-printed bioelectrodes.
This tackles the toxicity challenge, right? Traditional methods for printing conductive polymers often use toxic chemicals or high heat or high-intensity UV light.
Things you absolutely cannot safely use on living tissue or in a clinic. Right. The new method revolutionizes that. It uses water-soluble polymers that cure instantly under visible light. Simple LEDs, low-intensity lasers, which are perfectly safe for skin. This allows researchers to photo-pattern complex EEG electrodes directly onto living skin. They're calling it biostenciling.
That makes the sensor application fast, safe, and non-invasive. You could imagine applying a dozen diagnostic sensors to an emergency patient in minutes with just a flexible sheet and an LED light.
Exactly. It paves the way for temporary, high-fidelity biosensors that can be applied quickly in demanding clinical or field settings.
But eSkin, even if it's well-powered and safely applied, is inherently fragile compared to the rigid electronics we're used to. How do you make something that thin and flexible durable enough to withstand daily life?
This is all about solving the rigidity mismatch between soft textiles and rigid silicon components. The research team highlighted several solutions. For incredibly thin, complex multilayer electronics, they use atomic layer interlayers, sheets of material just a few atoms thick, to maintain flexibility through thousands of bends without cracking.
And for reliable wireless communication, which is crucial for streaming that ECG data, you need constant connectivity, even when the sensor is stretched.
That's where strain-invariant EMI shielding comes in. It's a metasurface, an artificially engineered material that maintains consistent electromagnetic performance, so you get reliable wireless communication, even under extreme deformation.
And I think the most creative solution cited in the sources for protecting components is the Cornell Orstitch development. It sounds like textile engineering meeting microelectronics.
Orstitch is brilliant because it leverages centuries-old textile techniques. It uses specialized embroidery to create self-folding 3D rigid structures within soft fabric.
So like tiny little origami bunkers inside your shirt?
That's a great way to put it. You create these tiny protected islands of rigidity within a smart shirt to house components like batteries or delicate chips. The overall garment is soft and flexible, but the critical rigid electronics are shielded from mechanical stress. It combines comfort with ruggedness.
It moves us closer to apparel that truly integrates computing power. So now that we have self-powered, durable eSkin, we can move to the interaction layer. Haptics, the sense of touch.
For years, VR and AR have had great sight and sound, but the touch feedback was rudimentary at best.
The ability to feel digital space is the final frontier of immersion.
And the miniaturization of touch is accelerating dramatically. We saw the breakthrough of the 18-gram haptic feedback ring. It features 3 degrees of freedom force sensing.
18 grams, that's less than a standard AA battery.
And this device uses an origami-inspired structural framework to deliver realistic, directional, tactile sensations for VR and AR, finally closing that sensory gap.
A device that's small, providing genuine directional tactile feedback is an enormous leap. And this isn't just about entertainment, it's about embodied learning and simulation.
The integration of professional-grade haptics into consumer simulation ecosystems like bHaptics, integrating with racing platforms like SimHub and Gran Turismo 7, is transforming the use case. The haptic vest transmits physical consequences.
Like subtle G-forces in a corner, or tire slip vibration.
Or the distinct kick of a gear shift, directly to your spine and body. It ceases to be just a game. It becomes a professional training tool. You perform an action, the vest instantly delivers the physical consequence, and a data logger records your reaction.
It creates this precise, closed-loop feedback mechanism for skill acquisition. It transforms abstract cues into actual muscle memory.
That is the definition of embodied learning mediated by sophisticated wearable tech. The body is the programmable surface.
This is truly mind-blowing stuff. We've covered the incredible speed and intimacy of this technology, but now we have to talk about the systemic risks and the legal frameworks trying to keep up. Before we move into the legal and regulatory side of this, let's just pause for a moment. If you're finding this insightful, whether you're listening to us on audio or watching the video version on YouTube, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly does help us reach new listeners and keeps this information flowing.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this week's breakthroughs in neural interfaces and electronic skin, especially that 100 millisecond reaction time. Okay, so we've established that technology is moving from an external accessory to an internal, hyper-intimate extension. And as the stakes for performance rise, the stakes for safety, privacy, and intellectual property just skyrocketed.
That's the crux of it. The technological advancement has outpaced the legal framework dramatically. The #1 existential threat to the wide-scale adoption of these strapped-in devices is the crisis of mental privacy.
We discussed the legislative push in Montana and Vermont to establish neuro rights. Now that thoughts can become hyper-reflexive actions in less than 100 milliseconds, what are the ethical implications of that conscious bypass clause being proposed?
The dilemma is profound. It's not about external behavior anymore. It's about the merging of intent and machine execution. The clause prohibits companies from using BCIs to execute decisions before the user has consciously committed to them.
So if my BCI augmented car predicts I'm about to slam the brakes and does it 100 milliseconds faster than I consciously intend to, who's liable if the prediction was slightly wrong?
Exactly.
Yeah.
Does speed justify the bypass of conscious will? These questions have to be answered before these technologies hit the mass market.
And then there's the inference loophole that our dedicated research team highlighted as the most insidious threat. If laws define neural data too narrowly,
Only covering direct brain recordings.
it ignores the vast amount of biometric data that can proxy your mental state.
Exactly. Let's create a practical scenario for you. A mass-market smart ring tracks your heart rate variability and skin conductance continuously. Our compiled data shows that advanced AI models can analyze these metrics to infer with high confidence that you're experiencing acute cognitive load and high stress between 3 p.m. and 5 p.m. on weekdays.
So what does a company do with that inferred mental state data?
They monetize it. A health insurance provider could use those patterns to adjust your risk profile. A marketing company could target you with anxiety-reducing supplements during those precise vulnerable windows.
And the company hasn't violated a neuro right law because they didn't technically read your EEG.
But they have harvested and monetized your involuntary mental state data. The focus needs to be on the type of data and the inference made, not just the source device.
So the battle over privacy might not be fought over the multi-$1,000 BISC implant. It's going to be fought over the $300 smart ring on your finger.
That's a crucial insight. And moving from privacy to market viability, we also saw huge moves this week from the FDA regarding clinical credibility.
Right. The regulatory bottleneck has always been that traditional pre-market authorization requiring years of static clinical trials is just too slow for this rapidly evolving digital health tech.
It is. The FDA's answer, as noted by the research team, is the Tempo Pilot technology-enabled meaningful patient outcomes. It's a voluntary program designed to accelerate access while maintaining rigor.
How does it fundamentally shift the model?
It employs a sophisticated trust but verify approach. It allows manufacturers of lower-risk devices to request enforcement discretion for certain traditional requirements, while simultaneously collecting and reporting real-world performance data from their deployed systems.
So instead of demanding a perfect static trial before deployment, the FDA allows the product to deploy faster, as long as the manufacturer rigorously monitors and reports on performance and safety in real time.
Precisely. It acknowledges that real-world evidence is often superior and more dynamic. And the Tempo Pilot is focused initially on complex areas like cardio-kidney metabolic conditions, musculoskeletal issues, and behavioral health.
This signals that regulators are finally treating wearables not as lifestyle gadgets, but as clinically credible, insurance-reimbursable tools, foundational medical infrastructure.
And that emerging infrastructure, especially the new form factors, is now being aggressively fought over in the courtroom.
Right. We move from regulatory change to legal warfare over form factor, specifically the battle of the smart rings.
This is high-stakes commercial drama. The U.S. International Trade Commission investigation involving Aura Health versus a massive list of competitors, including Samsung and Rincon, is defining the future of the wrist-worn interface.
Aura has adopted an aggressive legal strategy, filing a U.S. ITC complaint, and the core of it rests on their patent 11,860,178.
And that patent doesn't just cover the concept of a smart ring. It covers the essential engineering necessity, the design of a curved battery within a curved housing.
And why is that specific design so critical?
Because to make a smart ring small, light, and comfortable enough for 247 use, you cannot use a brick-shaped battery. You have to curve the battery along the circumference to maximize volumetric efficiency.
So by patenting the only efficient way to package power in a ring, Aura is trying to create a choke point.
They are either foreclosing the entire market or forcing competitors, including the massive Samsung, into compulsory licensing deals.
The stakes are astronomical. Aura is seeking a limited exclusion order in LEO, which could effectively ban the import of competitors' rings, like the anticipated Galaxy Ring, into the U.S.
This battle is defining who controls the default, continuous monitoring interface of the future.
And finally, as all this hyper-integrated clinical-grade hardware deploys, we can't ignore the gaping security void.
The research team repeatedly highlighted a dangerous paradox. The industry is building military-grade hardware on top of fundamentally consumer-grade software foundations.
We saw evidence of that this week with the December 2025 Android Wear OS Security Bulletin, detailing multiple critical Framework 0 days that are being exploited right now.
When the hardware gets this intimate, the consequences of a breach aren't just data theft, they're reality manipulation. This is the risk multiplier.
I mean, think about the stakes. A hack on a BCI could interfere with motor commands. An AR hack could overlay false information onto reality, a manipulated speed limit sign.
Or a false identity tag on a person. And a smart ring hack gives continuous, precise biometric signatures that reveal your real-time stress, sleep, and cognitive state, allowing for deep behavioral profiling.
The intimacy of the data and the access to the user's perception means the security has to be as sophisticated as the device itself. If the underlying software is weak, the entire augmented human experience is vulnerable. This has been an incredibly dense, fascinating, and sometimes alarming deep dive. When we look back at the sources compiled by our dedicated research team, the week of December 11th through the 18th wasn't just about incremental improvements.
No, it was about the maturation of foundational infrastructure that shifts the human-machine relationship forever. We can really summarize the week's consensus findings around the 3 I's.
Okay, first, invisibility. Devices are rapidly disappearing into the background. They're moving from bulky watches to high-style smart rings.
And then to seamless e-tattoos and even subdural BCI arrays. The key to continuous use is invisibility and comfort, letting you just forget the technology is even there.
Second, intelligence at the edge. AI is moving onto the device itself.
Whether it's the 3 mils latency chips in AR glasses, the on-device translation in utility glasses, or the self-powered sensors running analytics locally, the focus is on real-time performance and local privacy.
Minimizing reliance on the cloud. And third, clinical credibility.
Regulatory changes like the FDA Tempo Pilot, the ALS breakthrough designation, and medical-grade features like ECG and smart rings are rapidly shifting wearables into foundational, clinically recognized, and reimbursable medical infrastructure.
They're transforming from toys into tools.
And the convergence of all of this, high-bandwidth neural interfaces, low-latency AR, body-integrated sensors, it suggests a powerful conclusion. The focus has decisively shifted from what the wearable can do for the user to what the user can become with the wearable.
And here's where it gets really interesting. If technology becomes fully integrated with our physiology, achieving hyperreflexive control, seamless contextual awareness, and zero-burden energy, the ultimate product of this strapped-in era isn't a device, it's an augmented sense of self.
Which raises the final provocative thought we want to leave you with. If the human and the machine become seamlessly integrated, functioning as a single, enhanced entity, who owns the rights to our augmented experience?
Yeah.
And where exactly does the biological human end and the digital machine begin.
Thank you for joining us for this deep dive on Tomorrow Unveiled. We'll see you next week as we continue to unpack the future.